I think you can see my screen. Okay, so let me talk today about graph clustering. Okay, so suppose you are kind of given the data is in the form of graph, right? So this may arise natively, for example, in social network analysis where the links correspond to friendship relationships or who follows whom, and the weights may correspond to the strength of these relationships. Graphs may arise in many other different ways. For example, even in like selecting data for pre-training, you might have some graphs which talk about the similarity of different pre-training data, right? So a graph is vertices, edges, and we'll actually consider weighted edges, right? So for example, we might have weights on the edges, like I'm showing over here. So not just unit weights, but some real numbers, positive real numbers on edges. Okay. And so A is n by n, where n is the number of vertices. Okay, so A represents the weighted adjacency matrix of the graph. Okay, so in particular, Aij is equal to, let's suppose I have, sorry, Wij, if Ij is in the edge set, which is E, and if it is not in the edge set, we'll take it to be 0. So the edges, for example, that are missing, for example, between, there's no edge between the top left vertex and the top right vertex. And so that edge weight is 0. Okay. And what is the goal of graph clustering? Okay. So in some sense, what we are trying to do is we are trying to partition the edge set, the vertex set V into K clusters of nodes or vertices. Okay. So for example, if K is equal to 2, K could be equal to 2, then we have basically, I want to try to partition V into disjoint subsets. So V1 union V2. And I said there are disjoints, so V1 intersection V2 is the empty set. Okay. So in particular, for example, in this graph above, right, I can, if you think about what is the natural partitioning of these into two sets, it would be this would be one set, this would be the other set, because you can kind of see that the vertices on the left over here are more connected to each other than vertices across the boundary, right? And the way you can quantify it is you can actually look at this. Right? So suppose I now bisect or cut the graph into two by removing these two edges, right? Then the number of edges or the weights of the edges that I have to cut is small. Okay? So there is one over, so cut of V1 comma V2, where this is V1. V2 consists of these 4 vertices on the right. And this cut in this case is 2, which is 1 plus 1. This one over here and this one over here. Okay. And you can see that if I try to cut the graph somewhere else, right? So for example, if I try to cut the graph over here, right, then the cut is going to have much higher weight. In this case, it'll be, 2, 3, and suppose I had 1. Over here, then it would be, the cut would be at least 7 or 8. Okay. And so that's not a good cut. So what we want to do is we may want to minimize the cut. Okay. So this kinds of graphs arise in many different applications. Okay. So for example, social networks, they arise in kind of web data. For example, if I'm looking at the similarities between web documents, I can actually construct a similarity graph. It actually also arises in kind of image segmentation. So segmenting images, and not only in machine learning, but they actually arise in other applications such as circuit partitioning. And actually that's where a lot of this work happened, where the goal was to lay out a circuit on, so that's the hardware on a board. And what you wanted to do was put the circuit elements that had a lot of connections close to each other so that you did not have connections that were long, because that leads to kind of more power dissipation, right? So we define the cut between 2 vertices, V1 and V2, and that is summation of Aij. I belongs to V1, and so Vi belongs to V1 and Vj belongs to V2. So any questions so far? Is the notion, hopefully the notion of a cut is clear, right? So I'm basically trying to divide the graph, suppose k equal to 2, into 2 parts, so that the edges that I remove, if I remove the edges along the cut, that their weight is actually going to be small. So I can try to minimize, can try to minimize
I have a question on definition, if I may.
cut V1, V2. Yes, go ahead.
So on the definition, so I guess the E is like set of ordered pairs where I is connected to J. But then
Yes.
at A, do we really need E to define the graph? Because like
I could have just said that E is, I guess I could have said just that Eij is a weighted matrix.
right.
But generally, in graph theory, generally G is equal to V comma E. V is the vertices, E defines the edge set, which is the set of ordered pairs. And right now remember, we are only considering, I should have said that we are only looking at undirected graphs. And I'm just trying to reinforce the fact that the edges have weights by saying that Eij is some Wij.
Thank you.
Yeah, so it's not, I guess I could have, so that I'm basically going along with the conventional definition and then adding the edge weights to it.
I see. Thank
Okay.
you.
Now, you could try to minimize cut, but there are many graphs that appear in practice which may be like this. Okay. So when I say this, then it just means that, you have this one vertex over here, and if I try to minimize the cut, I'll partition it into this and this. And then somebody might say, hey, you know, the singleton node that you've cut into is not that interesting. Okay, so typically what happens is that if you just try to minimize the cut, it does not work well. So just minimizing cut V1, V2 does not work well because it leads to very unbalanced clusters. And when I say unbalanced, you can have different definitions of unbalance, but right now you can think of the number of vertices in the cluster. Okay. So one extreme kind of way to get around this, right, would be actually to enforce balance. Okay, so one classical way of enforcing balance is to do the following. I can say that I want to minimize the cut between V1 and V2, and assuming an even number of vertices, right, I would want the size of V1 to be exactly equal to size of V2. Okay. So this is basically now saying that I actually want my clusters to be exactly balanced. So we are going from one extreme where, you know, if we try to do it over here, right, we can get very unbalanced clusters, to a problem formulation where you actually enforce that the clusters are equal in size. Okay, and in some applications, this makes sense. In some other applications, it may not make sense. So we'll see how to kind of, you know, try to get around this equal balance in terms of exact equal balance. But this actually has been used in, for example, applications like circuit partitioning, right? And then one issue with this is that this criterion leads to an NP-hard problem, which means a pretty, you know, combinatorially too many possibilities, and so not easy to get the global optimum. As a result, people have come up with various heuristics, right? So one kind of historical famous heuristic is what's called the Kernighan-Lin heuristic. This is, by the way, the same Kernighan who was one of the inventors of the C language. Okay, so Kernighan-Lin heuristic, what it does is it starts with some partitioning. V1 and V2 such that V1 equals V2. So start with some balanced partitions, okay? And then what you do is you calculate change in cut if two vertices, one in V1 and second in V2, are swapped. So you do it for all the pairs. So you take V1, you'll take V2. For every pair of vertices in V1 and V2, you would ask the question, if I swap these vertices, what would be the change in cut? So clearly, by swapping the vertices, I will not change the balance, right? Because I started with the balance partitioning. And if I'm swapping vertices, I'll still maintain that the two vertex sets are equal in size. Okay, but what I can do is this now becomes a local search method, because if I'm not at the optimal, then there will always exist a pair of vertices that if I swap, then actually, I guess unless it is a local minima, that you will always have two vertices where if you swap, you will actually decrease the cut. Okay, so what this algorithm does is it then goes ahead and swaps the vertices. So swap the vertices that decreases the cut the most. Okay, and even if this does not decrease the cut by a positive amount, you could still do this, right? To basically to try and get out of local minima. Okay. Now, this is actually a simplistic version of the algorithm, right? In fact, the algorithm is a little bit more complicated, but I just wanted to give you the flavor. Okay. In fact, it actually performs a sequence of swaps. And it looks basically at a chain of swaps such that it decreases the cut the most. Okay, but I don't want to get into detail. I'm just kind of really giving it for historical reasons, because there are better methods which have been developed. Okay, so this Kernighan linear heuristic is a greedy algorithm. Okay, and even after this, more sophisticated methods were developed, but based on, local search or greedy methods. More sophisticated variants have been developed. In particular, there was a method by, two gentlemen by the name of Fiducia and Mathesis. Okay, and these were popular for circuit partitioning because this was the main application at that time. Okay, but what happens is that when you are talking about graphs that, for example, come up in social network analysis and so on, you don't necessarily want the vertices to be the two partitions to be exactly equal in size. For circuit partitioning, it actually makes sense because you are laying out the circuits on a board and you want to use the area of the board the best. And so it makes sense over there. But if you're trying to find groups of friends on a social network, right, where an edge signifies a friendship relationship, then you don't actually believe that the friend groups have to be exactly the same in size. So the next evolution of this graph clustering is to actually use something called weighted graph cuts. Okay, so the first is you look at ratio cut. And let me just write down the ratio cut criterion, right? So remember, we started off saying that you can actually minimize the cut. Okay, and now what we are saying is that the second part we said was we'll minimize the cut subject to exact equality. So there are two extreme ends, and ratio cut is somewhere in the middle. Okay, so it is not going to explicitly enforce the size of the vertices, right, in each of the partitions, but it's going to give a criterion which is the following. So cut V1, V2 divided by V1 plus cut V1, V2 divided by the size of V2. So it's called ratio cut because it's basically taking the ratio of the cut with the size of the vertices. And what you try to do is then you try to minimize overall V1, V2. And of course, if you look at this quantity, it is cut of V1, V2, right? That's the common thing, right? 1 by V1 plus 1 by V2. And that is cut V1, V2 times V1 plus V2 divided by, sorry, my writing is going all over the place now. Huh? Let me just write it properly. Sorry, I'm hovering towards the end of the page. So let me write it properly. Cut of V1, V2 times V1 plus V2 divided by V1, V2. Okay. And remember that V1 plus V2 V1 plus V2 is N. So this is cut V1, V2 times N divided by V1, V2. So that's one criterion. The criterion that I think actually is even better than this is what's called normalized cut. And sometimes I'll use RC of G, and sometimes I'll use NC of G to denote the normalized cut. And the criterion over here, well, similar. It's just a different way of normalizing the cut. So I'll still have cut V1, V2, but instead of dividing by just the number of vertices, I'll actually divide it by the sum of all the edges which are incident on V1. And I'll call that degree of V1. And I'll get to this, what this exactly is. Similarly, I'll have cut V1, V2 divided by degree of V2. Okay, so let me just define degree. So degree of V, let me just call it C. Okay, V of the vertices in a particular cluster. And that's exactly going to be equal to Aij, where Vi belongs to Vj, sorry, Vi belongs to Vc, and Ij belongs to the edge set. And we can actually also call it the links from Vc to all of V. So I've gone through actually quite a bit. Any questions? Maybe I'll just review it. Right, so we started off saying what is a good criterion for graph clustering. We said, okay, cut seems like a reasonable thing to do. So we want to try and minimize the cut. But if we just minimize the cut, we can actually get very unbalanced clusters. So one extreme way of enforcing balance is to enforce that the vertices are, the vertex sets or the clusters are exactly the same in size. This does make sense in applications like circuit partitioning, where there's a physical reason for making the vertices the same size. There are other examples where it also might make sense, right? And for that, people develop various heuristics. But then we started looking at a more relaxed way of enforcing the cuts, not to be exactly of the same size, but to have some balance through having this V1 and V2 be in denominators in ratio cut. And in normalized cut, we have degree of V1 and degree of V2 in the denominator. Okay. So just to kind of give you some notion as to where we are headed, we will actually look at this criterion and we will actually be able to relate it to a particular matrix, which is going to be called the graph Laplacian. It's the Laplacian of a graph. And it'll turn out that we'll actually be able to get clustering by looking at the eigenvectors of this graph Laplacian. Okay, the graph Laplacian is actually a pretty important matrix that comes up in graph theory. And what I'm basically setting up so far is, giving you some definitions of what it may make sense, how to divide a graph up so that the graph Laplacian will fall out very naturally.
I had a question.
Yeah, go ahead.
Yeah, so you said that using the min cut formulation would result in like unbalanced graphs, and I'm just trying to visually understand that. So like if you had like a graph where like maybe there's one node and it's only connected to like one other node, like would that be a situation where min cut would be bad? It would just cut off that single edge, causing like a
Yeah, so
wall.
I think that's exactly this scenario that we have, right? Because like this scenario over here.
But I mean, I guess in that situation it would make sense, right?
Well, what would make sense, sorry?
Like that clustering.
Yeah. So sometimes people will argue. So I mean, one is you could do min cut, right? But sometimes people will argue that it doesn't. Um, you're not capturing the spirit, right? That, for example, if I want to find two groups of friends, then in one case you have just one singleton vertex, and in the other case you have, all the rest of the vertices. It's not a very interesting. And the thing is that this kind of thing can actually happen quite a lot in, many graphs, right? So for example, if you look at social graphs, right, there may be some people who are just not very active, right? And so, you might, so for example, one of the reasons why this could be used is to actually do friend recommendations. This person is, let's say, new to the social network or hasn't really engaged with the social network, right? Then you want to try to get a group, right? So that you can recommend friends. And if you just partition this one vertex into a separate cluster, then you will not be able to do that.
I see. So like
Does that make sense or what?
yeah, sounds like it sounds like that's like an
Yeah.
outlier.
Yeah, so it's kind of like a little bit like an outlier, and in many of these cases, these these edges may not be kind of reflect the way things should be, right? So it could be that if this vertex corresponds to a person and they are in a social network, maybe they could actually have been friends with other people, but they just haven't.
Gotcha. Yeah, that makes sense.
Okay. Any other questions? Okay, so let me kind of just define kind of a few things, right? So we defined degree, which is links VC, comma V. Okay. I can also define links within the cluster VC. So I say links VC, comma VC. These are all the edges which are within the cluster VC. Okay, so VI, VJ belongs to VC. And of course, IJ belongs to etc. Okay. Now, the above is only valid for K equal to 2 clusters. Okay, but in practice, you might want to get more than 2 clusters. So how can you generalize the above definitions of ratio cut and normalized cut to K clusters? Okay. And it turns out that there is a pretty elegant kind of generalization, which is that you say that when I do ratio cut, then I'll have K partitions, V1, V2 through Vk. And in the ratio cut criterion, I'm going to try to minimize the following. C equal to 1 to K. Cut Vc to V minus Vc. So that's basically says the edges that are connecting Vc to the rest of the graph. And then I just normalize it by Vc. So you can verify that this is going to give you the exact same thing as this. Sorry, not this, but over here. Okay, when K equal to 2. Okay, because when K equal to 2, you'll have V1, V minus V1, which is exactly V2, divided by V1. And then similarly, you'll have cut V1, V2 comma V1, and the denominator will be V2 for the second term. Okay, so it makes sense. And then similarly, I'll have normalized cut. And that criterion will also be C equal to 1 to K, cut Vc, V minus Vc, divided by, now instead of number of vertices, it's the edges that are incident to vertices in V1. And what I would like to do in the normalized cut criterion is to minimize this ratio cut. Okay. So let's kind of look at this in a little bit more detail. When I say cut of Vc, V minus Vc, right? I actually kind of mean that this is equal to the links of Vc to V minus Vc. Okay. And that is equal to the degree of Vc minus links from Vc to Vc. Okay, so because degree of Vc will actually be the links of Vc to all of V, right? And then you're subtracting out the connections which are within Vc itself. Okay, so this holds. And the reason I've written this is that if I look at this particular quantity, right? If I now substitute this, right? That the cut is equal to cut VC, V minus VC is what appears in the denominator here. So if I then substitute degree of VC minus links VC divided by degree of VC, that becomes 1 minus links VC divided by degree of VC. So it's basically saying that, and you can actually call this criterion kind of, normalized association. Right? So you're actually, in some sense, if you're trying to minimize this, you're trying to maximize this. So minimizing, so that's a nice property. Okay, so minimizing the normalized cut is the same as maximizing normalized association. And I'm actually, this actually does not hold for ratio cut if you try to define something called ratio association. So that's a nice property. And I think it's really, and it is really related to the fact that, in normalized cut, both the numerator and the denominator are of the same type. So if you look at ratio cut, the numerator is actually talking about edges and edge weights, whereas the denominator is talking about vertices. Whereas the normalized cut is the numerator is about edge weights, and the denominator itself is about edge weights. So in some sense, it's very similar quantities, and that's why you have this kind of nice property, right? Which is that minimizing the normalized cut is the same as maximize the normalized association. Okay. So now we've written the criterion, right? And the goal is, how do we actually find, how do we minimize the ratio cut or the normalized cut? What we want to do is minimize these weighted. Sometimes I try to write too fast and mess up, okay? Minimize these weighted graph cut objectives. Okay. And what we will see is that many of you might have heard this term, spectral clustering. Spectral clustering is actually a pretty good heuristic that tries to minimize these objectives. And we will, in essence, be able to derive it. Okay. And, it's actually like a global heuristic. If you think about like the Kernighan-Lin heuristic, remember, first of all, that the problem is actually NP hard, right? So it's a hard problem. So you can't really get to the globally optimal solution. If you think about the Kernighan-Lin heuristic, right, it kind of just does these local exchanges. It's really a local heuristic. Whereas we'll see that spectral clustering looks at, eigenvectors of a matrix associated with the adjacency matrix and does partitioning based on that. And eigenvectors are kind of global properties of the entire matrix or of the entire graph. And so this is kind of like a small global heuristic. Okay, so we'll see that. Okay, so here is the algorithm. Okay, so here let me write down spectral. Well, maybe I won't write the algorithm right now, but let me just introduce some notation. Okay, and then we'll get to the algorithm. Okay, so one is what we'll do is we'll first associate, oh, too many S's and C's. We will associate an indicator vector and there are k clusters, so we'll have k indicator vectors. So y1, y2 through yk for each cluster. And each of these yi's is n-dimensional, and n is the number of vertices. Okay, so what do I mean by indicator vector? Let me spell it out. I'm saying that the jth component of yc is equal to 1 if vertex j or vj belongs to the cluster and 0 otherwise. Okay. It's just an indicator vector. It's a vector of ones and zeros. 1 if the corresponding vertex belongs to the corresponding cluster and 0 otherwise. Okay. So you can clearly see the following, that yc transpose yc is equal to vc. Because yc transpose yc is just counting the number of ones in this vector. And the number of ones is exactly equal to the number of vertices in this particular cluster. And more interestingly, if I do C1 transpose yc2, then this is equal to 0 if C1 is not equal to C2, which means that yc1 and yc2 are orthogonal to each other. Okay. So the reason this is kind of really interesting and important is that, remember, we are trying to find the optimal clustering. So right now we are just defining something. And what we are saying is that if you have these indicator vectors have a particular L2 norm, and these indicator vectors are orthogonal to each other. Okay, so let's now define other quantities. And then soon, I think this is the last quantity that I'll define, and then we'll be able to get to the actual algorithm. Okay, so I'm going to define a diagonal matrix D, and it's going to be the diagonal matrix of degrees.
Excuse me, a question here.
No.
So C1 not equals to C2 means like the VC1 and VC2 has a empty set
Intersection.
intersection, right?
And that's exactly, for example, when we talked about what it means for a clustering, right? Did I say right? So over here, like V1 intersection V2 is the empty set.
Okay, yeah,
And I should have probably mentioned that again, but even when we extended it to K clusters, we mean that, V1, V2 through Vk are all disjoint.
okay, I see. Thank you.
So that's the definition, classical definition of clustering. Now, you can start talking about things like overlapping clustering, but that's not what we are doing right now.
Thanks.
Okay, so we are going to define a diagonal matrix. The diagonal matrix is also, D is a diagonal matrix which is n by n. Okay, and it has degrees on the vertices. Degree of, and these are degrees of the vertices. V2 and degree of Vn. So remember, the degrees are the edge, sum of all the edge weights that are incident on that particular vertex. And all the other entries are 0 because it's a diagonal matrix. Okay. And now, what is interesting is that if I now do YC transpose, now instead of YC transpose YC, if I do YC transpose D of YC, then I'll pick up these vertices. So I'll pick up degree of V1 plus degree of VR, where V1, V2 through VR belongs to VC. Okay. R being equal to size of VC. And that is exactly equal to degree of VC. Okay. So I have this one. So what I'm trying to do is that, I have these things, right? And normalized cut. And I have ratio cut. I have these quantities. And then what I'm actually trying to do is represent it by, or make them, or show that they are actually equal to some operations, matrix operations with the indicator vectors. So I defined a matrix D, which was this diagonal matrix. And what I've shown is that YC transpose D of YC is degree of VC. Okay, and it turns out that if you do YC transpose A of YC, where A is the original weighted adjacency matrix, then this is equal to lengths of VC comma VC. Okay, let's see, let me just try to give a motivation of why that is so, right? So suppose I have, my matrix A. Okay, and let me kind of collect all the vertices which belong to the first cluster over here. Okay, so the whole notion of clustering is to try to make this matrix, you can think of trying to make this matrix block diagonal so that most of the non-zeros are over here, and these correspond to the cut values. And I want to try to minimize the cut values, okay? And then when I take YC, then this will be ones corresponding to these entries over here, and zeros for all the rest. And so when I hit it by YC transpose YC transpose, so if I look at this quantity, right, this is YC transpose and this is YC, what will happen is it'll basically pick up all of these vertices in V1. Okay? And as a result, it's actually going to be the sum of all these entries. And that's exactly the links of VC within itself. Okay? So in particular, Y1 transpose A of Y1 is going to be links of V1 to itself. So now let's see, let's look at these quantities. Let's look at RC, which is the ratio cut. Remember that we said that it is C equal to 1 through K, cut of VC, V minus VC, divided by magnitude of VC. Well, I wrote it before also as degree of VC minus links of VC comma VC divided by VC, right? And this is summation C equal to 1 through K. Now I can write it in terms of the indicator vectors as summation C equal to 1 through K. This degree is given over here. So I can write it as YC transpose D of YC minus YC transpose A of YC. And the denominator is this. And if you look over here, then YC transpose YC is this value. So now I basically represented those cuts and ratio cut just by in terms of some indicator vectors and some matrices. Okay, I can write this as summation of C equals 1 through K, YC transpose D minus A, YC divided by YC transpose YC. And that's basically how we get to this particular matrix, D minus A. Okay, and this matrix plays a very central role in graph theory. So L is, so sometimes we call it L. Okay, L is equal to D minus A is called the graph Laplacian. I can write this as YC transpose L YC divided by YC transpose YC. And this quantity is actually quite important. It's called the graph Laplacian. Okay, and L has various properties. Okay, and let's see, maybe I'll just list out a few of the properties, right? One can show that L is equal to EE transpose, where E is the node edge adjacency matrix or incidence matrix. Okay, and E is, number of vertices, N, and number of edges. And if I have an edge ij, it'll basically have square root wij minus square root wij in the ith location and the jth location. Okay, so just two entries per non-zero. But what it implies, forget about, exactly what this means. What it implies is that L is symmetric that you could have seen before. It also implies, because I can write it as E transpose, it means that it is a positive semi-definite matrix. Another property it has, so it has various properties. 1, 2, 3 is that L times the one vector. Well, L is equal to D minus A times 1. You can show that this is equal to the 0 vector. Okay, which means that the all ones vector is an eigenvector of L with eigenvalue 0. Okay. You can also show that for any vector x transpose Lx is equal to, well, x transpose EE transpose x. And you can convince yourself that this is equal to Wij times xi minus xj squared. So sometimes this property is used for doing kind of regularization on graphs, right? Where you are trying to maintain x values which are similar between similar vertices or neighboring vertices. Okay. So now remember that we showed that ratio cut of G. Sorry, I'm throwing probably a lot at you, but I think it's a useful thing to know. Graph Laplacian, because graph clustering actually can, or graph analysis can actually, is an important part of machine learning. So I didn't want to ignore it. Okay, so ratio cut was equal to this. Okay, it turns out that normalized cut G is equal to, let me just write it down first. C equal to 1 through K. YC transpose D minus A YC divided by YC transpose DYC. So there's a D which is different here, and it was not over here. Okay, so remember this was just YC transpose YC. Here I have D of YC. Okay, so this is equal to summation of C equal to 1 through K, YC transpose L YC divided by YC transpose D of S. Okay. And sometimes what you can do is you can, have ZC is equal to D half of YC. Okay. And if you do that, then YC is D minus half of ZC, and my normalized cut can be written as summation of C equals 1 through K, ZC transpose D minus half L D minus half ZC ZC transpose ZC. and d minus half L d minus half is called the normalized Laplace. Okay. Well, I guess I've kind of thrown quite a lot of things at you. So let me review them. Okay. So remember, we started off by talking about cut, talking about, introducing some balancing constraints. Those balancing constraints that the vertices are, or the clusters are of exact same size may not be a good constraint, right? So then what you can do is you can have these ratio cut and normalized cut objectives. I can define them in terms of things related to graphs, but then I can change everything to vectors and matrices. And I can just say that the problem of minimizing the ratio cut is the problem of minimizing this quantity, where L is the graph Laplacian. And what you try to find are the YCs. And what I want to do is find YCs such that this criterion is minimized. And you actually get something very similar with normalized cut, except you get this normalized Laplacian. Any questions?
But that E here is different from the E that we have at the start of the graph definition, right?
No, the E is the same. E is the same as this. This E over.
Yeah, but when we start defining the graph, E was
Oh, I'm sorry. Yes, of course. Okay, I realized that I made a mistake. I've overloaded E. Here, where I'm talking about E, it is the node adjacent incidence matrix.
right.
So E over here is this particular matrix, and early on in the lecture, it just meant the set of edges. Correct.
Thank you. Yeah.
Okay. So this leads to a very important algorithm, right? And that is called spectral clustering. Okay. So let me kind of give you the spectral clustering algorithm. Okay. So what it does is, given the graph, what it'll do is, and the algorithm is actually very simple, right? It'll form the graph Laplacian. Okay, which is L is equal to D minus A. Okay. Then what it will do is you want to try to minimize these quantities. Okay. So what it kind of says is that I'm going to actually drop these integer constraints on my indicator vectors, right? And I'm actually going to, if I drop them, then the quantities that minimize this are actually eigenvectors that correspond to the smallest eigenvalues of F. Okay, so let me write that down. Compute the smallest, okay, the k smallest eigenvectors of L. Okay, except the very smallest, because that actually doesn't give any information. Okay, as we saw that all one's vector corresponds to the zero eigenvalue. So the k smallest eigenvectors of L right? And the reason it is, remember that the eigenvectors have this property, right? Lx is equal to lambda x. Okay, this is what you get in ratio cut. Okay, so this is for ratio cut. Okay, and if you're trying to do normalized cut, you do d minus half LD minus half for normalized cut. Okay, because that corresponds to Lx equal to lambda dx. Okay, once you compute the smallest eigenvectors and you assemble them, in matrix Y. Okay, and remember that this matrix is now going to be n by k. So my matrix is n. This is the number of clusters, and each column is an eigenvector. So the second smallest eigenvector, the third smallest eigenvector, and the kth smallest eigenvector. Okay, and then what you would do is, so these vectors, essentially you can think of them as the YCs that we talked about, except there is no 0, 1 constraint on them. So now, given these vectors, you want to try to extract the 0, 1 constraint. So what you can do is, you have some way to extract the clustering from Y. Okay, and one way to do it is run k-means over the n rows of Y. Okay, so this is equal to 1. So the way you can think of it is the following. I construct this graph Laplacian d minus a, right? Then I construct, so minimize the ratio cut, I compute the smallest eigenvectors of L. If I'm trying to minimize the normalized cut, I take the normalized Laplacian. And then I compute the k smallest eigenvectors of this. Then I assemble them in this. I can think of the ith row of this matrix. Okay, ith row. Okay, and that corresponds to, you can think of that as a low dimensional representation, k-dimensional representation of the ith vertex. So from a graph, you've gone to a low dimensional representation of that, a vector representation, and then you can do things like you can run k-means over the n rows, and you'll get a partitioning of Y. Okay, so I know that I've gone through quite a bit, but I really wanted to motivate this kind of spectral clustering method. It's actually a fascinating topic, and you can actually study it for multiple weeks, not just over one lecture. But I wanted to introduce that to you and also show how it comes up quite naturally in graph clustering. Right? So spectral clustering, you're given a graph, you form this very simple quantity, right, called the graph Laplacian. You compute eigenvectors of the graph Laplacian, and you can actually extract the cluster. So this turns out to be quite a good heuristic. Okay, spectral clustering is a powerful global heuristic for No. Okay, any questions? Okay, so I did kind of want to introduce that during the class. So just going back to where we are at the class now, we did like the deep learning lectures and transformer lectures last time because I wanted to do them early so that you could be ready with your projects and so on. All of you or most of you have submitted your project proposals. We'll give them back to you. We'll go back to looking at, LLMs and the latest and greatest in, deep learning and machine learning in the next few lectures. What is upcoming is we will return we'll give you feedback on your project proposals, maybe ask for clarifications and so on, have a clear objective. And then we will assign you homework 4. So the remaining of the course is really going to be about for you doing the projects that you have chosen and also doing homework 4, which will essentially ask you to look at a language model.